All right, guys. Sometimes my students in the past, when I've taught, have told me that their favorite days are, well, actually, their favorite days are when it snows and I don't show up for school. But their favorite days when I actually show up are not days that I necessarily teach, but I just do problems. And that's kind of what we got going on here. I've got 11 problems that I'm going to run through with you, show you not only how to work these things, but how to think about them. So, and students, do they tell me oftentimes that they seem to get more out of this type of instruction than they do when I'm actually teaching, like, augmented matrices and things like that. So, guys, let's do it. Along the way, we're gonna use the calculator. I'm gonna use the overlay of the calculator today. So, I'll show you that when it comes up. All right. So, um, this let me kind of do this a little bit. All right. So this Jasmine chick wants to use milk and orange juice to increase the amount of calcium and vitamin A in her daily diet. An ounce, 37 milligrams. How many ounces of milk and orange juice? Okay. Now, when some students read this, there's just a lot going on, and they need to process the information. The first thing I tell students to do is usually you can go to the last sentence and identify what you need to solve. So for which you need to solve technically, but what you need to solve for. So I go to the last sentence and it says, how many ounces? So I know that my variables that I'm going to solve for have something to do with how many, right? I'm asked a question, I'm going to solve something, so obviously my answer needs to be what I'm being asked to solve. So how many ounces of milk and orange juice? So there's two things there. So the first thing I'm going to do is I'm going to identify my variables. And I'm going to let X be the ounces of milk. And I'm going to let Y be the ounces of orange juice. The next thing I'm going to do is I'm going to see that I have two variables. So I know right off the bat that I've got to look back into my problem and come up with two relationships that give me equations. Well, this is a situation where I get back to just a very simple premise that apples and apples have to be apples and orange juice have to be orange juice. Well, I can see that an ounce of milk contains 37 milligrams of calcium and 57 micrograms of vitamin A. Orange juice has so much calcium and so much vitamin A. Down here it says provide exactly 500 milligrams of calcium and 1200 milligrams of vitamin A. So let's focus first of all on this 500 milligrams of calcium. I know the calcium from the milk plus the calcium in the orange juice has to be the total amount of calcium. So my first equation is going to be for the calcium. So I have 37 milligrams for each ounce of milk. And again, I'm doing X is the number of ounces of milk. And then I have 5 milligrams for every ounce of orange juice. So I'll let that be Y. So my total calcium has to be 500. The next thing I'm going to do is I'm going to set up something for the other relationship that I'm given in there, or not necessarily a relationship, but the values, and that's the vitamin A. So I have 57 micrograms of vitamin A for each ounce of milk. And I have 65 micrograms of each vitamin A for each ounce of orange juice. I have a total of 1,200 micrograms of vitamin A. Now, I've got this set up, and I'll tell you, this part right here, the second part, is the hardest, because I've made it easy on you now with this whole augmented matrix thing. So the third step is to create an augmented matrix. Well, we saw from the previous video that the augmented matrix for this is going to look like 37, 5, 500, 57, 65, 1,200. So gang, if I put this into my calculator, I'm going to get the answer. So I'm going to use this calculator this time. If I can put that up there where... Yeah, that's not really too cool. Yeah, that'll work. So let's go second function into matrix. And I want to go over to edit first. It turns out I need a 2 by 3, so it's already set there. So I need 37, 5, 500, 57, 65, 1,200. Now, before I go any further, I like to just stop and take a deep breath, because I don't want to do everything right so far and then just make a stupid typo and end up missing. So I just go back through and check my 37, my 5, my 500. Just make sure that my values are correct. All right, second function quit. To get out of that, I need to go into this second function matrix. Go over to math, just like I showed you in the previous video. Come up to B, which is RREF. Go back to matrix and get my matrix A. Close it up with the right parentheses, and I get my values 12.5 and 7.5. Well, the 12.5 came first, so we've got our solution here, 1, 0, 12.5, and 0, 1, 7.5 from the calculator. And I don't know if you can read that or not, but this is the solution. So this right here stood for my x, because remember that we had our x's and our y's. So the first the first column was my x, the second column was my y. So this tells me that x equals 12.5 and y equals 7.5. Well, guys, since I clearly back in step 1 identified what this tells us, that x is the ounces of milk, I know that my solution is 12.5 ounces of milk and 7.5 ounces of orange juice. But guys, that's the solution to the first problem. And you can see that by learning how to do augmented matrices, that it makes the solution part of that very, very, very easy. Let's get into another type of problem. All right, so a small manufacturing plant manufactures riding lawnmowers. The plant has a fixed cost of $48,000, variable cost of $1,400. The mowers are sold for $1,800 each. Find the cost function. This is really, really easy, because There's really not a quantity given. It's actually just you have your fixed and your variable cost provided. So we need 1400 Q, which is our marginal cost or variable cost, and our fixed cost is 48,000. Easy stuff. The revenue function, R of Q, is just the amount that this lawnmower is sowed at times the quantity that is sowed. Now, set up a system of linear equations and transform your system into augmented matrix form. Now, what we're ultimately thinking about here is I want to let this over here be thought of as my y in both cases. So if I set this up as y equals 1400 Q plus 48,000, and this is y equal 1800 Q, what I could do is I could visualize this as what I've done before and kind of flip this to let well, I don't really want to flip it. What I want to do is I want to get it in a form that I've seen before, and that would be something where I have everything with my variables on one side and everything without my variables on the other side. So I could make this y minus 1400 Q equals 48,000. And I can make this one y minus 1800 Q equals 0. So again, I'm trying to learn from the past and trying to see that I usually have x minus y equal a number, x, y equal a number. So I want to get everything with my variables on one side and everything with my numbers on the other. What this allows me to do is allows me to set up the augmented matrix 1, negative 1400, 48,000, and 1, negative 1800, 0. All right. Now I'm going to put that in my calculator, and I'm going to use the calculator on the screen here for this one. So I'm going to go into matrix, go over to edit. I want to set this up as a 2 by 3. So I have 1 minus 1400, 48,000, 1, negative 1800, 0. Now take a deep breath, look back, make sure everything is set like it should. So I'm going to go second function, quit. I just did this for the previous problem, so I need the same command, just with different numbers. And I get something like this. And I'm going to write this down. I have 1, 0, 0, 1. So I have 216,000. And I have 120. All right, so I've written this down. Now I'll go back over and try to help you decide what this tells us. Okay? Now, so, guys, first of all, what was in the position of the columns? Over here, the columns were what? That was my y's. And my second column were my q's. So this was my quantity. So the second one right here tells me when my quantity is 120, my y is 216,000. But what did I do with this y? I made my cost and my revenue both y's. So if I have y equals y and I have my revenue equals my cost, which are what may equal to my y's, what does this tell me? Well, this tells me when my R of Q and C of Q are the same value. So guys, what we found here is nothing more than the value when R of Q equals C of Q, which is the break even. So it's just a kind of a fancy schmancy way of coming up with the break even point like we did before. Okay, now let's try that out. Before I told you we would find the break even point algebraically. And that's where the revenue equals the cost. Well, let's see. We had revenue is 1,800 Q. Cost was 1,400 Q plus, I don't remember, 48,000. Subtract the 1,400 Q from both sides. Divide by both sides by 400. So it tells us there that we have a quantity of 120 for the break even, which is exactly what we found back over here. But we'd have to put the 120 back into either the revenue or the cost, and it's going to be easier to put it in the revenue. So take 1,800 times 120, and you'll see that we get $216,000. This would have been equivalent if we had taken the cost of C of 120 which would also be 216,000. So that tells us when we sell 120 units that the cost at 120 units is the same at 216,000. So you can use augmented matrices to come up with a little fancier stuff. Well, you don't come up with fancier stuff. You just come up with actually maybe a little more sophisticated way of coming up with the answer. All right, gang. Here we have two different companies. And I told you earlier about drivers and putters for left hand and right hand. So apparently what's going on here, you've got two different companies, a plant A and a plant B. Let's say this one's in Ohio and this one's in Kentucky, just to give you some sort of reference potentially. Production costs for each instrument are given in the following. Plant A is matrix A, and Plant A is matrix B. So guys, at the end of the day, I say that a lot, don't I, at the end of the day. Matrix A looks like this. And matrix B looks like this. So guys, that 125 tells us what? That the production cost for the labor for each banjo at Plant A is $125. So apparently the labor for banjos and the labor for guitars is cheaper the way I've set this up in Kentucky, and I just randomly chose that. But it's cheaper for Plant B. Okay, so what we want down here is we want 1/2 A plus B. Well, guys, the A plus B part is really simple. We have two 2x2 matrices, so we're going to add the corresponding parts. So that looks like 103. This looks like 81. This looks like 174, and that looks like 240. So if I take half of that, half of 103 is 51.5. Half of 81 is 40.5. Half of 174 is 87, I hope. And half is 120. So guys, that's all you had to do in that problem. So that gives you an average cost of production in each plant. Now, it's important to notice that this sum, this average cost of production keeps the same format as these. So this was material, this was labor, and this was for guitars, and this is for banjos. So the average cost of materials for a guitar for plant A and plant B is 51.5. So the structure of the sum of the matrices stays the same, and then the corresponding parts mean the same thing. All right. Now, guys, this is a place where this is probably the most important problem I'll do in this video. The others are important, but this one really focuses on something that's important. So what it does is right here. We've organized our measurements here. So matrix M gives the protein, carbs, and fat for cereal A and cereal B, and matrix N gives cereal A and cereal B of mix X, mix Y, and mix Z. So the question here is, does M times N exist? Well, we can look at M and we can see that M is a 3 by 2 matrix. And we can look at N and see that this is a 2 by 3 matrix. So these two numbers have to be the same, and the product matrix will be a 3 by 3. So yes, it exists, and the product will be a 3 by 3. Now let's come down here and look at N by M. So N is a 2 by 3, and M is a 3 by 2. So yes, it also exists. But does either product mean anything? Now, guys, let me explain what I mean by that. And again, this is huge. This is probably the most important thing I'm going to teach in this video. What we got here is both exist, but are either meaningful. Do either have a meaningful interpretation. So the way you determine this is our first matrix A times our second matrix B in general. Now again, remember, this is we're just going to call this an M by N, and we're going to call this an R by S. For the product to exist, N has to be equal to R. But guys, when we get into applications, we need to know, are they meaningful? Must measure the same thing. Okay, now let me tell you what I mean by that. Let's go back here and look at the first the first situation. Okay, guys, I know this gets a little, this is more complicated. This is the hardest thing that we're going to do in this video. Now, right here, we see that MN does exist. But when I take M, I have proteins, carbs, and fat, and I have cereal A and cereal B. When I take this matrix in, I have cereal A, B, but I have mix X, mix Y, and mix Z that come from these. For this product to be meaningful, not only do the number of columns, the 2 right here, have to be equal to the number of rows right there, but they have to measure the same thing, and they do. They're both measuring, they're both give values for the type of cereal. Therefore, when we create the product matrix, the rows, there's 3 right here, not only the values come from using the rows of the first matrix, the interpretation comes from using the first matrix. Same thing here. The interpretation comes from the columns of the second matrix. So for example, when we multiply these two values, these two matrices together, this value, whatever number goes right there, is going to tell us the total number of carbohydrates in mix Y. So these values are going to be meaningful. Now, let me give you an illustration of where it wouldn't be meaningful, and where we can't interpret. Let's change it. Let's put this over here. So what I'm doing now is I have taken N times M. Now, arithmetically, if these are just generic matrices, I can multiply those because this is a 2 by 3. This is a 3 by 2, so these values are the same. But for the the elements of the matrix to be meaningful, to have some sort of meaningful interpretation, what we're measuring on the columns has to be the same thing that we're measuring on the rows, and it's not. This is a mixture. This is protein, carbs, and fat. So arithmetically, we can put these or mathematically, I should say, we can put these matrices in our calculator and hit multiply. It'll give us a value. It's just these entries in here don't mean anything to us because the condition of what the rows are measuring on the first matrix and what the columns are measuring on the second matrix doesn't coincide. So it does exist, but it's not meaningful. So guys, at the end of the day, the very first part A, we ask MN, and let's just create our own matrix here, if you will. Does MN exist? Yes. Is it meaningful? Yes. Because our columns and our rows, our columns of the first matrix, our rows of the second matrix are measuring the same thing. NM, does it exist? Yes. Is it meaningful? No. Our interpretations don't mean anything because the columns of the first matrix and the rows of the second matrix are the same number. There's 3 of each, but they're not measuring the same thing, so the interpretations are not meaningful. So gang, what I want to do is I want to go in and I want to find the matrix. So the easiest way to do that is use your calculator. So let's do that. So what I would do is I would come in and I would set up, I mean you can use M and N, but I'm just going to let matrix M be the first matrix. So I need a 3 by 2. So I have 4, 2, 20, 16, 3, and 1. All right. Now, second function quit. Go back into matrix. Scroll over to edit. We'll come down to B and we'll set it up as the N matrix. Now, guys, this is a 2 by 3. So we have 15, 10, 5, 5, 10, and 15. All right, let's get out of there. Now, what is relevant? Let's do A times B, which is the M times N. We know we're going to get what? A 3 by 3 matrix. So A times B. So guys, we know from what we saw earlier that for example, I concentrated on that center number, 360. So that would be the number of carbohydrates in mix Y. Because again, one more time, all right, I'm going to be redundant here because this is harder stuff, okay? When we put our first matrix, we had protein, carb, fats for AB, cereal A and B, and then matrix N, we had cereals A and B, but we had this mixture X, Y, and Z. We have a 3 by 2. We have a 2 by 3, so this stuff all matches out. But not only does it have to match out in number, it has to match out in what it's measuring. If it does, then our product matrix comes from these two things. We know from this that it's going to have 3 rows, and this information is going to come from the first matrix. This is going to have 3 columns, and its information is going to come from the columns of the second matrix. So I have a 3 by 3 P, C, F, X, Y, Z. So that value that we saw in the middle on our calculator, which was 360, and I'm just going to write all these down. Now, if you're sitting here watching these videos and you got reruns of Friends on or Seinfeld or whatever, it's probably not going to work. This is going to take more thought than you giving this half of your attention, or maybe not even half. This is harder. Okay. So, for example, that 30 right there tells us what? The grams of fat in the mix X. Now, the other doesn't work out. It doesn't work out that way because the columns of the first matrix and rows of the second matrix are the same number, but they're not measuring the same thing. All right, guys, example number 5. We have an outdoor amphitheater. It's 25,000 seats. Ticket prices are $8, $12, and $20. Number must equal the number of the desired return is how many of each type of ticket. All right, so go to the last sentence. And the last sentence says how many of each type of ticket. Well, I go back into my problem now, and what kind of tickets do we have? Well, we've got the $8 tickets, we got $12 tickets, we got $20 tickets. So I'm going to let X be the number of $8 tickets. Y is going to be the number of $12 tickets. And I'm going to let Z be the number of $20 tickets. All right, gang, what we got? 3 variables. This tells us that we must arrive at 3 equations. Well, one of these is really easy. This outdoor amphitheater, which consists of $8, $12 tickets, and $20 tickets, is $25,000. So guys, I know that the sum of all of these numbers of tickets has to be $25,000. The next thing, it tells me that the money has to be $320. So if I think about the number of $8 tickets I found, I can find the revenue of those by taking 8 times the number I sell. I can get the revenue from the $12 tickets by taking 12 times the number of those that I sell. And I can take the 20 times the number of $20 tickets I sell. And I know that has to be $320,000. Now, sometimes a lot of students will say, well, I'm done, but you're not done. Guys, you got 3 variables, x, y, and z, so we must end up with 3 equations. So we've got to look back at our problem and find another relationship. And we see in this sentence right here, the number of tickets priced at $8 must equal the number of tickets priced at $20. So the number of tickets at $8, we've let that be x. That must equal the number of tickets priced at $20, which we've let be z. Now, a lot of students will say, well, I'm done. Well, you're really not done, because we need to put this in a form that leads us nicely into an augmented matrix. So I have x plus y plus z equals 25,000. I have 8x plus 12y plus 20z equals 320,000. And then this one down here, x's and z's, I've got to get these in x's and y's and z's and numbers. I've got to appreciate, respect, if you will, the column situation. So I've got my x's on the left side of the equal sign, so I can put that there. I don't have any y's. And when I bring this z across where it needs to be on the left side of the equal sign, I have negative z, and I'm going to have nothing left over here. So gang, my augmented matrix is going to look like 1, 1, 1, 25,000, 8, 12, 20, 320,000, and 1, 0, minus 1, 0. All right, so let's put this in our calculator, just like before. So I'm just going to choose matrix A. We need a 3 by 4. So I have 1, 1, 1, 25,000. Just make sure you get your zeros right. I need 8, 12, 20, 320,000. And the one that usually throws people off, the 1, 0, minus 1, and 0. All right, let's get out of this. Now, I know somewhere previously I've done that RREF thing, so I'm going to go second function. It's going to give me that. Well, I don't want that one. Let's see if I did it the line before. Do it again. And there's what I need, so I don't have to go back through all that stuff. So when I get this, I see that my solution tells me what? Well, this first line right here tells me that my X, which is the $8 tickets, is 5,000. This second line tells me my Y's, which was my $12 tickets, was I need 15,000 $12 tickets, and I need 5,000 at the $20 tickets. So I wrote all this down over here just because that's what I do. All right, so you can see that I've done the solution right here from the output on the calculator. And it works out right. All right, we need everything to add up to 25,000. So 5,000 plus 15,000 plus 5,000 is 25,000. We need the number of $8 tickets to be the same thing as the number of $20 tickets, which we do, 5,000 each. And you can go ahead and multiply this out. You can go 8 times 5,000, 12 times 15,000, and 20 times 5,000. And you'll see you get 320,000 as the total revenue. All right, I don't care what you say. That is the easiest way to do that problem. All right, gang, I'm learning here now. You should learn a little bit, and what should we do first? Go to the last sentence. How many ounces of cottage cheese and yogurt? All right, so I'm going to let X be the ounces of cottage cheese. I'm going to let Y be the ounces of yogurt. You can almost always go to the last sentence because that's the way questions are posed. It gives you all your information, and then it'll come in and say, how many of whatever you're looking for. It makes sense that the variables that we solve for coincide with what's being asked in the question. That's just good old common sense in my opinion. Now we got to look into the problem and see what kind of relationships we have, okay? Well, we can see that each ounce of cottage cheese has protein and calcium. Each ounce of yogurt has protein and calcium. And then down here we have a total for protein and calcium. So I'm going to have a protein equation. And I know I'm going to have a calcium equation. So I'm going to circle these. I have 3 protein and 1 protein has to be my total protein. Apples plus apples are apples. Oranges plus oranges are oranges. Protein plus protein is protein. I have 16 milligrams of calcium. 41 milligrams of calcium has to be my total amount of calcium. Augmented matrix. Grab your calculator. Gang, what size do we need here? We need a tube of 3. 3, 1. If I'm going too fast for you, pause me. Take still shots. Just don't indict me on anything. All right, gang, we got it. Quit. I'm just going to use what I did before. That's what I need. So I see right now that I need 16.65 ounces of cottage cheese. And I need 12.04 ounces of yogurt. Now, I have to tell you, when something turns out like this and it's not a nice answer like 16 or 12, I am tempted to check out my work because I just want to make sure that I've done everything correctly here. So the first thing I'm going to look at is I'm going to come in and look at my matrix A and just make sure I typed everything in correctly. So I can access my matrix A and I see that I had 3,162 and I had 1641,760, which corresponds to what I had right there. Okay. Now I want to make sure I didn't make a mistake in creating this. So I needed 3 and 1 and 62. I needed 1641 and 760, which I have. So guys, even though it didn't turn out right, I feel good about this answer. I've added, protein plus protein to get protein, calcium plus calcium to get calcium. I have my columns equal to cottage cheese, which I need. I've got this column equal to my yogurt, which I need. Guys, I trust that final answer. All right, gang, this one looks like something we did before, right? Cost function, we're given fixed costs and variable costs. So guys, that is really easy. So we have 24,000 plus 7.45Q. We sell these things in $19.95. Guys, I don't know why, but so many students I've seen in the past want to do that right there. And that's just wrong. I mean, if you wake up tomorrow and you want to do math wrong, do this. You'll get it all wrong. The revenue is a function of the quantity. And if you don't have a variable here, you have no quantity. That's just telling you whatever quantity you have produced, the revenue is always going to be 19.95. Well, guys, that's not what we have. We have a Q there because for each additional unit we sell, we get $19.95 more. So again, what did I do before that worked? Think about these as Y. So I didn't leave myself much room to write, so I'm going to come down here. So we get Y equals, and I'm going to put my guys, that stuff ain't gonna work. You got to have structure. You got to have this the variables on one side, the numbers without the variables in another. Now I'm going to set it up where I put my Q's first here, and that's perfectly fine. So this is going to be minus 7.45Q plus Y equals 24,000. And I'm going to go minus 19.95Q plus Y equals 0. So gang, my augmented matrix is going to look like minus 7.45, 1, 24,000, minus 19.95, 1, 0. Let's put that in our calculator. Again, I'm just going to use A. Need a 2 by 3, so this is minus 7.45. And all that's going to happen here is our interpretation of our values are going to be flipped. All right, does everything look good? No typos? All right, because we can all make typos. I don't care who you are. So I want to quit that. I want to go back. I need to go further than that, so I hit it again. And I see I did this. Numbers have been changed, so it's going to be cool. So guys, what we got here is the following. I'm going to write this down. All right. So when I come back over here, here's what I've got down at the bottom. Well, this is telling me that whatever variable I have in the first column, and notice that I set up the Q's here, right? So this is telling me that when my quantity is 1920, that my Y's is 38,304. But guys, I set my Y's up to be my revenue and my cost. So guys, that tells me that's my break even. That tells me when I sell 1,920 quantity that my revenue and my cost, definition of break even, is $38,304. All right, let's see if we learned anything from previous stuff. In a local California election, a public relations firm promoted this candidate 3 ways: phone calls, house visits, and letters. We get a cost per contact, and we have it in 2 cities. All right. Does MN exist? Well, M is a 3x1, and N is a 2x3. Got nothing to do. Nope. Not even consideration. Not even close. Does that exist? All right. Does NM? Well, N is a 2x3. M is a 3x1. So it does exist. But is it meaningful? Well, let's examine the structure, okay? We have a 2x3. Berkeley, Oakland. Telephone. House visit. Letter. This over here is a 3x1. Telephone. House visit. Letter. Cost. Not only is there 3 of these and 3 of these, they mean the same thing. Our resulting matrix is going to be a 2x1. It's going to get its rows from the first matrix, Berkeley, Oakland, and it's going to get its value for the column from the second matrix. So guys, when we multiply this out, and I'm not going to do it just to save time, it's going to give us the total cost for Berkeley and for Oakland. The interpretation is also meaningful because the columns not only are the same as the rows, the columns on the first matrix and the rows on the second matrix, but they actually measure the same thing. And you know what? I want to be thorough here. If you want to fast forward, you can. I want to be thorough here and go ahead and do that just because I need to. All right, so guys, first matrix, I'm going to let that be the end matrix. So we need a 2x3, which is what we got. So 15, 10, and 5. And 5, 10, and 15. Okay, so let's quit. Go back into matrix. Let's go over and set up the second matrix, B. So gang, here we need what, a 3x1. 4, 20, and 3. All right, boys and girls, let's matrix A times matrix B. So guys, your total money spent in Berkeley for the total of telephone, house visits, and letters, $275. The total amount spent in Oakland was $265. All right. Well, this is interesting. You know, did I just do something silly? All right. I don't really see a reason to work this problem again because we just worked it. See previously. I think we can work that one, can't we? Yeah, we just worked it. That's kind of weird. All right, couple of harder problems. I mean, not really harder, just something else going on here. This one's kind of hard. What if you had 3x plus 1 equal 4? What would you do? You'd start here, would you? You wouldn't start with the term that has the variable. You'd start with this and move it over here. Well, guys, that kind of makes sense here. 1, 2, 1, 1. x1, x2. And when I move this over here, I'll go 9 minus 3. And 9 minus 4 to be 5. What's going to happen next? Well, from the previous video, we saw that we would multiply 1, 2, 1, 1 times its inverse. And we would have to multiply on the left over here because matrices are not commutative, as I discussed ad nauseum before. What happens right here when you multiply a matrix times its inverse? Essentially, you get 1. So this tells me that x1, x2 can be found by taking 1, 2, 1, 1 inverse times 6, 5. Guys, I'm going to let this be my A. I'm going to set this up as my B. So let's go do it. So gang, A needs to be a 2 by 2. So 1, 2, 1, 1. Guys, all square matrices don't have inverses, but the ones we encounter will have. And let's go get matrix B and set it up. Matrix B needs to be a 2 by 1. That's going to be a 6 and a 5. Alright guys, so what we need to do here is we need to go matrix A, inverse, times matrix B. So the answer would be 4, 1. All right, now this is a little harder, a lot harder. Let's see what's going on here. This is more challenging. So this actually makes you think not about multiplying matrices with your calculator, but how do you actually multiply these things using the linear combination we talked about, I think, a couple of videos again. So it says find a squared. So I know that a squared is a times a, which in this problem is ab, times b squared, minus a squared, minus ab. Now if you're one of those students like me, you probably want to try this before you see it to see if you can get it done. If you're probably the A students. So just pause the video and see if you could figure this out. And then once you think you've got it, come back and then you could play the rest of the video and see what happens. Well, first of all, keep in mind that you have a 2 by 2. So, for obvious reasons, we can definitely multiply these things, and the product matrix is going to be a 2 by 2. Now how do we get, this is row 1, this is row 2, this is column 1, this is column 2. How do we get this right here? We take a linear combination of row 1 from the first matrix with column 1 of the second matrix. So we're going to take AB times AB plus B squared times negative A squared. What happens here? Row 1, column 2. So row 1, column 2. AB times B squared plus B squared times negative AB All right, I've got a phone call coming in. I don't know who that is. Let's see. So that's going to be negative AB cubed. All right, this is going to take row 2, column 1, so I'm focusing on row 2, column 1. So I got negative A squared times AB. And then I take row 2 times column 1. So I'm going to have plus A cubed B. The next thing I get is row 2, column 2. So I have row 2, column 2. So I have negative A squared B squared. And then I have negative AB times negative AB, which is positive A squared B squared. So gang, what does this turn out to be? A squared B squared minus A squared B squared is 0. AB cubed minus AB cubed is 0. A cubed B minus A cubed B plus A cubed B is 0. And minus A squared B squared plus A squared B squared is 0. So guys, it turns out that regardless what your AB is, if it's in this form right here, it's going to give you an A squared that is 0. So let's just choose something randomly. Let's say A is 3 and B is 5. So A times B would be 15. B squared would be 25. Negative A squared would be negative 9. And negative A times B would be negative 15. So let's put that into our calculator. So it's a 2 by 2, so we're set. So I want a 15, a 25, a negative 9, and a negative 15. So guys, for any A and B we choose, when we take matrix A and square it, we're going to get 0, 0. Guys, nothing holy about 3 and 5. This 3 and 5 that I chose, it didn't matter what A and B I chose. I could have chosen A equals negative 2/3 and B equals positive 1/7. Doesn't matter. A times B, B squared, negative A squared, negative AB, square that, 0, 0, 0. Guys, that's all I got for you. That's the last